Work done and energy stored in an elastic substance. The energy stored in an elastic substance is called elastic potential energy. This energy is used to do work in an elastic substance. The work done is equal to the elastic potential energy. But we know work done to be equal to force times distance covered in the direction of the force. Therefore, work done in an elastic material is equal to the average force times the extension or the compression produced. Work done, represented by W here, is equal to the average force, which is half F, times the extension or compression, represented by small letter e, which is equal to half Fe. This is our equation 1. From Hooke's law of elasticity, the applied force is equal to the product of the force constant and the extension. K is the force constant. Therefore, the work done on an elastic material is equal to half Ke squared, equation 2. In a force extension graph, the work done when a force F1, which produces extension E1, is increased to force F2 that produces extension E2, is the area of the shape under the line or curve which links the points in the graph, as shown below. In this force extension graph, the force F1 produced extension E1, a higher force F2 produced a longer extension E2, and this is represented by this graph. From this graph, the work done is equal to the area of the shape under the line between points A and B. And this shape that has been shaded here is trapezium. Therefore, the work done is equal to the area of trapezium A, B, C, D. If the extension occurs from point 0, that's the starting point, to A, as shown in this graph, from here to here, then the work done is equal to the area of this triangle here, from triangles OAD. And that area, we know the area of triangle to be half base times height. Therefore, the work done is equal to half F1 times E1 for this case. Example 1. A spring of force constant 1500 Newton per meter is acted upon by a constant force of 75 Newton. Calculate the potential energy stored in the spring. Option A, 1.9 joules, B, 3.2 joules, C, 3.8 joules, and D, 5.0 joules. The solution to this problem is as follows. Solution. From the question, we are provided with the force constant of the elastic substance, and that's 1500 Newton per meter. We are also given the applied force F as 75 newtons. We are asked to calculate the energy stored. The energy stored is the elastic potential energy. So this energy is obtained using half Fe, E being the extension, or we use half Ke squared. We can see from both formula that we need the extension E. So we can get that extension by applying Hooke's law equation. Applying Hooke's law equation, we have F is equal to KE. 75 is equal to 1500 E. E will give you 75 over 1500, which is 0.05 meters. With the extension obtained, we can now calculate the elastic potential energy. Therefore, PE will give me half FE. That will give me half times the force 75 times 0.05 in joules. The potential energy will now give us 1.875 joules, which is approximately equal to 1.9 joules. By this solution, option A is correct. Option A is correct. Example 2. The diagram below shows the force extension curve of a piece of wire. The energy stored when the wire is stretched from E to F is dash. Here is the force extension graph. A force of 0.1 Newton from the graph gave extension of 0.05 meters. Also, a force of 0.2 Newton produced an extension of 0.1 Newton. With other information, this graph was obtained. Now, option A, 1.5 times 10 raised to power minus 2 joules. Option B, 7.5 times 10 raised to power minus 2 joules. Option C, 2.5 times 10 raised to power minus 3 joules. Option D, 7.5 times 10 raised to power minus 3 joules. The solution to example 2 is as follows. The energy stored is equal to the work done in the wire, work done on the wire. And that work done is equal to the area of the shape PQFE. That shape is that of a trapezium. Therefore, work done is equal to half the sum of the parallel size times the height. That's the formula for finding the area of a trapezium. That will give us half 0.1 plus 0.2 times the height, which is the difference in the two extensions, 0.1 minus 0.05. So the work done will be 0.5, that's half, times 0.3 times 0.05 in joules. The work done is equal to 7.5 times 10 raised to power minus 3 joules. By this solution, option D is correct. Option D. Example 3. A catapult used to hold a stone of mass 500 grams is extended by 20 centimeters. with an applied force F. If the stone leaves with a velocity of 40 meters per second, the value of F is dash. Option A, 4.0 times 10 raised to power 4 newtons. B, 4.0 times 10 raised to power 3 newton. C, 2.0 times 10 raised to power 3 newton. And option D, 4.0 times 10 raised to power 2 newton. The solution to this problem is as follows. First, we must note that the catapult is the elastic substance. Catapult is equal to elastic substance. The energy stored in the catapult, that is the elastic potential energy, is imparted or given to the stone to move. Elastic potential energy of catapult equal to energy of motion of the stone. Kinetic energy of stone. So we have half Fe, that's the potential energy, is equal to half mv squared, while the potential energy is half Fe. So half we cancel out on both sides, we are left with Fe is equal to mv squared. F is unknown. The extension is 0.02, that's 20 cm converted to meters, is equal to 0.5, that's the 500 grams, converted to kilogram. Okay, let's start from there. 500 over 1000, that's in kilogram, times the velocity 40 squared. So we have 0.2 F will give me 0.5 times 1600. 0.2 F will give me 800. So the force applied is 800 divided by 0.2. That will give us 4000 Newton, which is the same thing as 4.0 times 10 raised to power 3 Newton. By this, option B is correct.